In this lesson, we're looking at solving problems involving permutations with restrictions. So that is where determining restrictions will affect the number of possible outcomes. So we're looking first at general restrictions, then grouped items, identical objects, and then finishing off with objects arranged in a circle. So the general idea, as you can see here with general restrictions, is that when considering permutations with restrictions, we deal with the restrictions first. And general restrictions are relating to specific choices in positions. So it could be looking at the number of possibilities or the number of arrangements of the characters in the word dog, where the D must be first. Okay, so we can see that's pretty straightforward when we're looking at those number of arrangements. If the first one must be a D and the other two are free, there's only one option for the first, as it must be D, and then we have two possibilities and then one possibility. So this is we're looking for 1 out of 1, and this is we're looking for the arrangements of 2 out of 2. So number of arrangements would be 1p1 multiplied by 2p2. And that would be 1 factorial multiplied by 2 factorial, and our outcome is 2 possibilities. If we take this a little bit further and we look at an example, how many arrangements of the word Darwin begin and end with a vowel? So we can see that the restriction here is that the first and last letter must be a vowel. So if we set this out, we've got 1, 2, 3, 4, 5, 6 letters. The first and last must be a vowel, and then everything else in between is free. So we've got 2 vowels, so that means that this could be 1 out of 2. This is 1 out of the 1 remaining for the vowels, and then the remaining is 4p4. And so that means our number of arrangements will be 2p1 by 4p4 multiplied by 1p1, which is 2 factorial over 2 take 1 factorial, so 1 factorial multiplied by 4 factorial multiplied by 1 factorial, which is 2 by 24 by 1, and so we've got 48 possibilities that begin and end with a vowel. So then when we look at B, and we're looking at using the digits 0, 1, 2, 3, 4, and 5 without repetition, how many odd 4-digit numbers can you form? So with this problem, we could start with an odd, or we could start with an even, and that means we have to break it into the 2 parts, so number of odd on the first, or number of even in the first spot. So we've got 4 digits, 1, 2, 3, 4, or 1, 2, 3, 4. So as we split this up into starting with odd or starting with even, because they will give different numbers of possibilities. If the first and last must be odd in this case, then there's initially 3 odds and there's 2 odds left for the last value, and then there's 4 values left to fill the middle. So this would be 4 and 3. So 3p1 and 2p1 and 4p2. When we look at even, we can't have the 0 as a first value, so there's only 2 possibilities here. We need to have an odd for the last, so we've got 1, 2, 3 possibilities. And then we have 4 possibilities left for the remaining, so we've got 4 and 3. So this must be even, this must be odd, and this is the remaining. So we've got 2p1, we've got 3p1, in the middle we have 4p2. So this would become 3, 3 by 4 by 3 by 2, and 2 by 4 by 3 by 3, which will give us 36 by 2, which will be 72, and 9 by 8, which will be 72, and we have 144 different possibilities. There's two scenarios where we're looking at general restrictions with varying difficulties, a little bit more strategy in the second example, but the idea being the same. We have to adjust for the restrictions first, and then we determine the number of possibilities. When we're looking at grouped items, the thought is that if we're grouping things together, we can treat them as one item. So if we've got 1, 2, 3, 4, 5 items, and we're saying that these 3 items, let's say this is 1, 2, 3, and we've got 4 and 5, these 3 items must be grouped together, then the total number of possible arrangements will be 3p3. So we're only arranging 3 items, and we have to multiply by the number of different ways that we can rearrange a 3 within that group. And so we'll multiply by 3p3 as well. So in this case, we're grouping 3 together, and we're treating this as one item. So it's a product of the arrangements including the group multiplied by the arrangements of the group. And that's pretty much our scenario whenever we're looking at grouped items. So in this example, we can show how that works. The first example, how many arrangements of the word equals are there if the vowels are kept together? So we know that there's 1, 2, 3, 4, 5, 6 letters, and they're all unique and different. The number of vowels is 1, 2, 3, and the number of consonants are 3 as well. So the vowels we're grouping and we keep together, so we treat as one. So number of arrangements will be 4p4 with the consonants and the vowels as a single value, and then we're multiplying by 3p3, which is a number of different ways we can arrange the vowels. Arrangements including the group, and this is arrangements of the group. And so our total number of arrangements are 4 factorial multiplied by 3 factorial, which is 24 multiplied by 6. And so 24 multiplied by 6 is 120 plus 24, which is 144 different arrangements, if those vowels are kept together as a group. Now when we look at part B, we've got 2 chemistry books, we got 4 physics books, and we have 5 bio books, and we want them to be arranged on a shelf with each subject kept together. That means we've got 3 different groups. So we've got one group, we've got another group, so the second group, and we've got our third group. So a total number of arrangements here will be, if we're keeping them all as groups, we've got 3 values, and then multiplied by the number of ways we can arrange a chem book, so that's 2p2. Number of ways we can rearrange the physics books, which will be 4p4, and the number of different ways we can rearrange the bio books, which will be 5p5. So a total number of possibilities will be 3 factorial multiplied by 2 factorial by 4 factorial by 5 factorial, and that is 6 by 2 by 24 by 120, and that is 34,560 different arrangements. So there's 2 restrictions. We've looked at general restrictions in position, and we have looked at restrictions where we've got grouped items. The next restriction is when we're looking at identical items. Now, the simple way to think about this is, if I've got 4 objects, let's say I've got a red and 3 blues. All the 3 blues are identical. If I look at the number of arrangements disregarding the fact that they're the same, and I look at 4p4, which is 4 factorial, and I've got 24 different arrangements, For every arrangement, so the differences will be the positions of red. I'll have red and 3 blues. I'll have the red in the second position, and then the 3 blues. I'll have the red in the third position, and the 3 blues. Or I can have the red in the fourth position, and the 3 blues. So, although we've calculated this out, and it says there's 24 different possibilities, because these blues are identical, for every position, there will be 3 factorial different arrangements that will have to be disregarded. So if this is blue 1, blue 2, blue 3, this 4p4 or 4 factorial takes into account the arrangements of these blues. Now we want to get rid of that as a possibility. So with every one of these, we've got 3 factorial arrangements where we adjust these blues. In order to discount that, we want to divide by that 3 factorial. So that means the true number of arrangements will be 4p4, but over the number of ways that we can rearrange the identical items. So in this case, it will be 3p3. So we're looking at 4 factorial over 3 factorial. So there's only 4 possible arrangements, which is a conclusion we came to before. Okay, so that's our general rule. We're saying that for every identical item, we need to divide by the number of ways that we can rearrange them. So we will say that the number of arrangements is our number of total arrangements over the number of arrangements of identical items. Okay, so it's pretty straightforward. Let's look at an example. So we want to find the number of permutations of the letters of the word riffraff. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. We have 8 letters, but we have 1, 2 R's, and we have 1, 2, 3, 4 F's, and we want to find the number of arrangements. So the number of arrangements will be our 8p, 8, we're rearranging 8 letters, and we're dividing by the number of arrangements of the identical letters. So this will be 2p2, which will account for the R's, and 4p4, which will account for the F's. So we've got 8 factorial over 2 factorial multiplied by 4 factorial. So that leaves us with 8 by 7 by 6 by 5. The 4 factorial will cancel, and we're over 2. So that cancels down to 4 and 1, and our final answer is 840. When we look at B, we've got 4 identical knives, 3 identical forks, and 2 identical spoons in a drawer. They are taken out of the drawer and lined up in a row. How many ways can this be done? So in total, we've got 4 plus 3 plus 2. So we have 9 objects. And in there we have 4 knives, 3 forks, and 2 spoons. So the number of arrangements will be 9p9 over 4p4 by 3p3 by 2p2. And so that's 9 factorial over 4 factorial, 3 factorial, 2 factorial. And the total number of possibilities is 1260. Okay, so you can see it's pretty easy dealing with identical objects. If they're identical, we divide by the number of ways that those identical objects can be arranged. When we take this a little bit further and we look at a problem-solving scenario, we've got a grid that consists of unit squares. By traveling only right or down along the grid lines, how many paths are there? So hopefully you can see that we can have any combination of rights and downs. And we could go 1, 2, 3, 4 down, and 1, 2, 3, 4, 5 across, or any combination of that. So what I would suggest is that we've got 9 movements that have to occur, where there's 4 downs, which are identical, and there's 5 rights, which are identical. And so therefore the number of arrangements, or the number of different ways that we can get from point A to point B, would then be 9p9 over 4p4 by 5p5. So that's 9 factorial over 4 factorial 5 factorial. And we end up with 126 different ways of going from A to B. Okay, so pretty practical application. How many different ways from point A to point B, only using these movements, and we can shortcut that process quite significantly. The last thing we're going to look at is object organized in a circle. So the general rule is that it's NPR over the number of objects. So let's say we've got A, B, C, D. Now, the thought is that because a circle doesn't have a starting or an ending point, this arrangement A, B, C, D will be the same as A, B, C, D, and also the same as A, B, C, D, and A, B, C, D. So those 4 arrangements are identical, as there's no start and end point to a circle. So therefore it makes sense that for every given arrangement, all arrangements, we need to account for the number of R positions, which are identical. Okay, so it just comes down to that. The number of arrangements is equal to NPR over R. That makes a very simple calculation when working with arrangements in circles. So we'll go through these examples nice and quick. The first one is, by recalling the appropriate formula, given an expression for the number of different arrangements, if, from a group of 8 people, 5 are to be seated around a table, then we know straight away that our number of arrangements we've got 8 people, but 5 sitting around a table, so it will be 8p5 over the number of seats, which is 5. So we'd have to divide by the number of different arrangements for every layout. Part B, we want to evaluate that. So number of arrangements will be 8 factorial over 8 take 5 factorial, which is 3 factorial, then all over 5. So that will be 8 by 7 by 6 by 5 by 4, all over 5. And so our number of arrangements will be 8 by 7 by 6 by 4, which will be 1344. And when we look at part C, it says each table received 1 lucky door prize and 1 lucky seat prize. Determine the probability of the same person at one table winning both. So our probability in this case of winning both will be the number of ways we can win once over the number of ways we can win both. So winning once has just 5 possibilities, 5 different people, and winning both, there's 5 people or 5 people, so we end up with 5 on 25, which is 1 on 5. So that doesn't really link to our table scenario so much. We're just looking at a probability application of this problem. Our last example is, at a dinner party for 10 people, all the guests were seated at a circular table. How many different arrangements were possible? So in this scenario, we're assuming that all people are seated. So that means it will be 10p10. And we're dividing by 10, which is the number of seats around the table. So that means we've got 10 factorial on 10, and we end up with 9 factorial. 3, 6, 2, 8, 8, 0 different arrangements. Okay, so that concludes our lesson. Hopefully you can see the difference between those specific restrictions. So it comes down to having a strategy for general restrictions, grouped items, identical objects, and then objects arranged in a circle. And of course, any combination of these or combination with different addition and multiplication rule scenarios. Okay, thank you for listening to the lesson.